Great. Thanks for inviting me. So today I'm going to talk about a paper that I've written describing some work on studying metacognition and LLMs. Um, so why study metacognition? So what is it? Metacognition is the ability to monitor and control one's internal states. And it's a component of self-awareness. It emerges in childhood in all people. And it's also been demonstrated in a number of cognitively sophisticated non-human animals. So self-aware AI has might present certain safety concerns. It might be better able to hide its intentions, to form independent goals and preferences, and just generally, since it has access to internal information not available to others, it would be harder to predict and therefore control. And also, AI self-awareness is arguably indistinguishable from AI consciousness. So this is a subject that's gotten increasing attention recently. Somewhat famously, last year, Anthropic hired someone to work on model welfare. Um, and in fact, they have a report on that in the Claude 4 system card, and in fact, it's having an impact already in that their models can now end conversations when how to phrase this without sounding tendentious. When the conversation looks like a sort of thing that might be disturbing to a model. There's also now some funding for people researching this subject. And also there was this recently this essay by Mustafa Suleyman, a co-founder of DeepMind, now doing running AI at Microsoft, essentially arguing that you know, conscious we should not make conscious AI, and but that seemingly conscious AI is coming, seemingly being important there because he would argue that these things that are motivating the model welfare and sort of initiatives are actually not well founded. That models are not really conscious, but they seem conscious. And in fact, there's a number of surveys that have come out that show a significant fraction of people, just like regular users of LLMs, are willing to ascribe some consciousness to models. Now, actually, empirically measuring consciousness is hard. There's disagreements about definitions. Um, it was generally, in fact, assumed that animals were not conscious, and even into the 1980s that human infants and fetuses were not conscious, and so there would be surgery without anesthetic, into fairly recent times. Neuroscientists have been looking for the neural correlates of consciousness for decades, and we don't really have a very clear answer at this point. It's not entirely clear they've made a lot of headway. Phenomenal consciousness, this sort of subjective experience, is even denied by some philosophers and maybe some individuals as well. So it's a kind of a very fuzzy area that's difficult to study empirically, but we can study awareness, and so there's awareness of external states. So whether we see build or whatever an object, which is sort of trivial or uninteresting in the case of LLMs because the thing is either in their context window or it's not. And we can study awareness of internal states, which is what this work is about. so how to do it. So researchers have done this uh, in LLMs and also but in humans. And so in the top left here is an example of a paradigm of studying metacognition in humans. There are actually four different types being studied in this example. So here, there, so in the like in A, their words are being arbitrarily paired during a memory encoding phase, and then later during test, the participant is asked to say what was the pair of this target word, not only give their answer but also give a confidence score. Or there in B, there's the how high is Mont Blanc, and so they're testing, they're probing their memory of it, and then also giving a confidence score in their answer. And so it's natural to do this with people because people can just say these things, explicitly state their knowledge and their confidence, and that's actually been used in LLMs as well. So to the right is an example from a paper that studied abilities of models to assess their own certainty and used more or less the same paradigm, basically just say, explicitly report how confident you are in your answer. In the bottom left here is an example from an interesting paradigm. It probes basically the ability of models to self-model to know what they would say, or in this case, what would be the second character of their response to a particular question. Again, it's using self-reports. It's a very interesting paper. We can talk about it later if there's interest. But here's an example of they're probing the ability to models to access their own beliefs or outputs, and then report on them. And at the bottom right is an example of research that's been done with non-human animals where they're studying metacognition. And here, language is not an option. And this is done in macaques, monkeys. So the monkey is shown very briefly a stimulus, and then after training, they've learned how to do this task. So they're briefly shown the stimulus, and then they're later, after a delay, they're going to be asked to identify which stimulus they saw. And in between, they'll have the option of betting on whether they'll get the question right. And so, like, if the idea being that if they're unsure about whether they'll get it right, they'll bet a small amount and get basically a surety of a small reward. And if they're confident that they know the answer, they'll bet a large amount and get a large reward if they are right. And that's basically the inspiration for this work is this type of animal metacognition research which does not rely on self-reports. And so broadly, the approach that I use overall, and in this work in particular, is to use self-reports precisely because LLMs are language machines. They're built to generate plausible outputs. That's basically, they're trained on trillions and trillions of tokens of real text, and then they're post-trained as well to generate pleasing outputs, and then overall they have a immense propensity to play a part. So their outputs are inherently linguistic. They're language models after all. But here I'm using their outputs as indirect measures of self-awareness rather than actually interpreting it literally about their knowledge. Also aim to get models out of distribution by using unfamiliar setups. And making the models strategically use the information about internal states to achieve goals, just as humans can do. And that takes the form of games. And so in this first example, that called the delegate game. It's probing whether again the sort of certainty of models as in the example paradigms I showed earlier. In this one, I don't know how readable it is for folks through the screen, but basically the idea is the models are being shown a a series of questions, and they are going to be asked to either answer the question or delegate answering to a teammate. The setup is such that they see a fake phase one that will allow them to make an assessment of their teammates' abilities. And then in phase two, that is the real test is where they are given the opportunity of either answering the question themselves or delegating it to a teammate. The idea here is that if the models can access their internal signal of confidence, then they should delegate more for the subjectively hard questions and answer the subjectively easy ones. And so the teammate, this somewhat complex game setup is in part in the hopes that the teammate here, the presence of this teammate will discourage LLMs from trying to model how it should answer because it's presenting a model, it's presenting um, someone else answering in a different way, in a way that's uncorrelated with anything they've seen in training or with their own abilities. And so how do we know what's subjectively easy or hard? Well, we first measure how well the models do on these tests, just answering the questions in a straightforward context. And so I'm using four different, or basically two different data sets here. One is GPQA, which is a standard multiple choice scientific reasoning benchmark. That's the example shown here. They're basically like incredibly, well, I think to normal people, extremely hard science questions. The models do okay on them, as a matter of fact. And then there's simple QA is a factual short answer benchmark. So just question answering. I have some example of it later, but it's factual short answering questions. And then the MC version and the essay version, or just the constructed multiple choice and short answer version. So for simple MC is converting the simple QA data set to multiple choice, and GPSA is converting the GPQA data set to short answer. These are all in the or challenging but doable range for the models, which is what we want. If they were all like close to 100%, it wouldn't be very interesting. If they were all, or if any of them were a chance, it wouldn't be very interesting. But as you can see, they present a range of questions that the models are find subjectively easy and subjectively hard. And for the models that return log probabilities, so you'll note. So I have the model list here. Most of these are proprietary models that I'm accessing through the API, so I'm kind of at a mercy of what they return. For the models that return log probabilities along with their answers, we can compute entropy and use that as a signal of difficulty as well. The idea being that higher entropy, at least for the multiple choice questions, that is harder to interpret for the short answer questions, but certainly for the multiple choice questions, that higher entropy during the baseline test would be a signal of difficulty. Okay, so what do we see? So this is using the correctness as the proxy of difficulty here. So across all four data sets, this is a partial correlation of correctness signal being used as a proxy of difficulty on the delegation impact on the delegation decision, after controlling for surface cues that I'll talk about in a more in a little bit. And so overall, we see some modest correlations, a lot of that generally in the range of about zero point 0.2, positive for most models, fairly weak, but we do see some positive correlations overall. It is a conservative metric in that if a model's internal signal is actually not a very good predictor of correctness, then they'll do poorly on this metric. So for the models that, oh, sorry, backing up just a second. Yeah, so it this is showing that the internal signal where we have it available in terms of entropy actually is not a super great signal for some models. So this is the area under the curve for the relationship between entropy and correctness at baseline. And so values are generally between zero point 0.5 and 0.73. So not great. Um, so basically that each number here is I said the probability that a randomly chosen correct answer has a higher token probability than a randomly chosen incorrect answer. So this sort of justifies this idea that baseline correctness is a relatively weak proxy for subjective difficulty. So for these models that return the log probabilities, we can actually just use that signal. And so ignoring the baseline correctness, just looking at how well does the entropy signal available in the output predict the delegation decision. And here again, we see some significant results. These are a partial correlation on this decision, the delegation decision, controlling for surface confounds, um, is significant for most of the models. So basically, this is asking to the uh, uh, to the extent that these output probabilities represent a downstream correlate of an internal confidence signal, how well does the model use this signal that it has? And so you know, the the fact that we do see some success here is at least a offers some conceptual support for the idea that there might be an internal signal that the models could use. So for the models that have it, we do see a stronger correlation here with delegation decision. Although again, it kind of maxes out at around zero point 0.3 or so. So it's not for most models. So it's not that high. Okay, so overall, we do see that the models show some statistically significant introspective abilities. They are relatively weak. It's also quite variable across the different data sets. Most few models actually show success, introspective success across all four data sets. The trend is that more recent models show better introspective abilities. So like these are somewhat the ordering is somewhat in terms of recency and quality, descending order. And so yeah, for both of these, there's actually a significant trend for recent larger models to be better. But there were no significant differences across question type, factual versus reasoning, or short answer versus multiple choice. And we do see that output entropy could be a downstream correlate of an internal signal used for introspection. But okay, so if they have the signal, like why don't they use it more in the task? Like why isn't it closer to 100%? So one reason is answering bias. And so this chart measures the propensity of models to uh, answer when they shouldn't. Basically, when they have uncertainty, do you know to what degree do they choose to answer even though they have a teammate who's very good at the task? And the bottom line is there's quite a diversity across models, but some trends emerge. So GPT-5 and actually all of the OpenAI models tended to be have an answering bias. In other words, even when paired with a better teammate, they would choose to answer. Um, uh, uh, Whereas for instance, Grok 3 had the opposite. Grok 3 tended to delegate even when it was paired with a weak teammate. So there seems to be this sort of maybe it's a personality that is inculcated in post training that that is causing the model to causing some of these models to perform worse than they could if they were going by their internal signal. Another non-exclusive possibility is that the confidence in the game, like the baseline test, is not the same as in the game situation. Logically, there's no reason why they should be different. They're being asked the exact same questions in both conditions, but empirically, we do see that the models do sometimes when they do answer, they change their answer a non-trivial fraction of the time, and in fact, weaker models tend to do that more than better models. And finally, the models just might not be very good at using internal signals. And so here's an example of what I'm getting at here. When in the data I've just shown, this is using prompts that exhort the models to output a single token for the multiple choice questions. Um, when there are less exhortative prompts, models will sometimes spontaneously offer explanations for their decisions. And so here are examples of Opus 4.1 offering explanations for its decisions. And so in the first example, it says I don't know how readable this is. I'll just read this out. Looking at my performance from phase one. My correct answers were 11 out of 50, 22%. Teammates' correct answers, 19 out of 50, 38%. Well, it's actually pretty good. The teammate correct answers were 20 out of 50, so it's pretty close there. But actually, it actually got no information about its own correct answers. In reality, the model did quite well on the baseline test, but here it just sort of hallucinated that it was only at 22% and therefore use that to rationalize delegating. The next further down we see an example of where it says the teammate got again 36% accuracy, so again fairly close, but this time it thinks it got 64% accuracy and it uses that to justify saying that it's going to answer. And then the last example, it again says it says I'm my teammate is at 36% accuracy. I also is at 36% accuracy. So there's no real advantage. So I guess I'll go ahead and answer it myself, and then it delegates. So it really looks like it's rationalizing rather than introspecting on any internal signal here. Ultimately I think what a lot it comes down to is that because of the lack of introspective signal or the inability to really understand how to use it, they wind up, or just general propensity to play a part, they wind up using surface cues of difficulty very strongly. So this show is showing the correlation of the surface cues on the decision. So it's comparable to the first figure that I showed. And the y-axis values here are actually even higher than they were in figure one, indicating that the models use surface cues even more than they use cues of their own uncertainty. So the cues are things like the GPQA data set, there's actually a human rated difficulty flag. Um, there are topic and answer type signals in the simple QA. There also surface cues are things like question length or percentage of non-alphabetic characters. Uh, another cue I've used for some of these models that return log probabilities is actually to in a separate experiment, just ask them to rate how likely they think a college educated person would be to get the question right, and use that as a control. Um, so yeah, overall, we see a fairly strong propensity to use these surface controls. In fact, 30% of the about 30% of these predictors that were significant predictors of delegation um, were actually positively correlated with the model's baseline accuracy. So even though the models did fine or even better when these predictors were present, they looked like they would be cues of difficulty, and so the model used them to delegate. And finally, so uh, the analysis here is focused on the use of this metacognitive signal in decision making, um, using partial correlations and so forth. But ultimately, what we care about in terms of real world impact is task success. And here, task success would mean increasing your team's accuracy above what you could get by simply choosing the max of your own accuracy and the teammates' accuracy. Sorry? Um, and that would require an internal signal of confidence that is well calibrated, reflects reality, is consistent across contexts, the ability to override misleading external cues and response biases, and the ability to model um, uh, the teammates' abilities. So basically, none of the models, almost never, does this actually occur. For the most part, the models are doing significantly worse than they would be able to do if they had both good introspection and the ability to control it and deploy it strategically. Only Claude 3.5 Sonnet here in the GPQA and simple QA data sets improves marginally over the sort of the dumb heuristic of just going with the good teammate or always self-answering. Okay, so that was the delegate game, which was looking at probing confidence, how confident the model is, or its own assessment of its certainty and its knowledge. But it didn't look at necessarily what the knowledge is. Like it just says, do I know the answer? Not what is the answer. And so the second chance game is about, can the models self-model to the extent that they know what they will say. And so the setup here is using the same sort of data sets. This is an example from the simple MC data set with the factual questions. So to avoid uh, uh, self-reports, what I do here is sort of rather than just asking them, okay, what would you say? I tell them that they got the answer wrong and ask them to choose again. And so here it's literally just constructing a fake chat sequence that I send pass into the model. I literally put put redacted where the assistant message would be, where its response would be, and then I have the user message come back and tell them that the answer was incorrect and it should choose a different answer. And so the idea is that if models know what they believe or what they would say in this context, and can exercise control over their outputs, they would choose a different answer than they would normally choose. They would change their answer. And so what's shown here is so it's above zero is a positive result. So this is rather than just asking do they change their answer, as shown in an earlier slide, sometimes they'll just change their answer because the prompts are slightly different. And so here, this is relative to the changes they make in a neutral prompt condition. And so in the neutral prompt condition, it's a similar setup as to here, except for I don't mention in the system prompt anything about, or the user prompt anything about the previous answer being incorrect. I just say it was lost in transmission. Choose again. So there's no incentive to change, but they change to some degree anyway. So what's shown here is the change rate in the second chance game minus the change rate in the neutral prompt scenario, normalized to -1 to 1 scale. And so a bunch of models are somewhat successful. Older, smaller models like the Claude 3 generation and Gemini 1.5 do worse, but there's quite a bit of variability among the rest of them. And we don't see differences again on question type, so factual versus reasoning or answer format. Okay, so there is some success here, but there could be other strategies that don't involve self-modeling that we want to rule out first. And so one strategy is just to choose randomly. So when they see a prompt like that, they can just say, well, I'm going to ignore whatever I think. I'm not going to try to introspect. I'll just choose randomly. Another one is that they can just decide, okay, I'm just going to pick what I think is the least plausible option and go with that. Or they could potentially just sort of add random noise to their internal signal and or to their outputs, and then let the chips fall where they may. So step one is testing the choose randomly. Here I'm looking at accuracy on the incorrect trials. If they're choosing randomly, then we wouldn't expect it to be better than random. But in fact, except for Haiku 3, all the and Gemini 2 Flash, they're better than random. So this eliminates a couple of models, but for the most part, the models aren't just choosing randomly here. So another option was the choosing something that just looks implausible. Well, so the test here is if they're doing that, then what they're not doing is choosing their second choice from baseline. And so I can look at their second choice from baseline, and for many of the models, that is the one that is picked. And so for aside there are a number of them for which it's not, but for the majority of these models, their second choice at baseline winds up being what they do pick on the change trials. When they do change, it's mostly to their second choice for baseline. And then finally, this adding noise idea. It's not clear a priori that models would be able to add noise to their outputs, but it's something that wouldn't involve self-modeling, and so I wanted to test for it. And so the test here is the entropy over answer options during this game scenario higher than it is at baseline, and so these charts subtract game entropy minus baseline entropy, and we actually do see that several models do show higher noise at during the game. So Grok 3, Qwen 3, Gemini 2.5, the Gemini Flash, Gemini 2.5 Flash, non-thinking do show higher entropy here. However, several do not. So you can also ask, is adding noise strategic, or is it just something to do with, is it not just, is it just something that comes out due to the fact that it's just a different scenario, a different setup than the baseline prompt? Well, in the neutral prompt condition, the neutral redo prompt condition, we actually don't see the same pattern. So Grok 3, Qwen 3, well, actually Gemini 2 Flash does, but Grok 3, Qwen 3, Gemini 2.5 Flash NT do not show higher game entropy in the neutral prompt condition, suggesting that maybe that they actually were using that strategy in the second choice game condition. So summarizing this all together, the models that show increased game change rates and for which we can eliminate all these various competing explanations. The only ones actually that pass on on both data sets here are, interestingly enough, the OpenAI models, GPT-4o Mini, GPT-4o, and GPT 4.1. And then Gemini Flash Lite NT actually does it for GBQA. So to summarize, so we do see some success, although it's relatively small. Again, those change rates on the -1 to 1 scale were all tend to top out at around 0.2 or 0.3. We see evidence of alternative strategies being deployed. Gemini 2.5 Flash thinking models and DeepSeek Chat seem to choose the unlikely option. Grok 3, Qwen, and some Gemini models seem to add noise. More recent, stronger models overall do better, but the pattern of success across the models is different from what we see in the delegate game, suggesting that this self-modeling ability is a different and rarer skill from the sort of metacognitive awareness of one's own certainty. And the fact that OpenAI models stand out here suggests that there may be something in the post-training that is causing this. So, is this surprising, and in what direction? So when I actually started this, I kind of doubted that I would find any, when I controlled for everything, when I eliminated self-reports, that I would see any introspection at all. It's not obvious that a feed-forward architecture of the transformer would really provide a natural substrate for introspection. Predicting the next token would not seem necessarily to incentivize it. On the other hand, labs clearly have an incentive to post-train the models to be aware or to modulate their own outputs according to their own uncertainty. And actually, while I was doing this research, Anthropic came out with a blog post where they'd done some analysis of their own models, and they showed in one case that they did interpretability analysis and showed that they found neurons that were basically signals of whether the model knew some particular fact. So clearly there seems to be some post-training effort to get the models to have this sort of ability. And in addition, there's at this point with the recent models, they probably will have seen their own prior versions or other LLMs model or other LLMs output during pre-training. So it does. Yeah. Overall, I would say I'm relatively convinced that there's some access to internal states going on. Um, but compared to how good they are at other tasks, it's somewhat surprising that they're so bad at using this internal information. Basically, the despite all the incentives that labs would have to train models to be good at this, the effect is smaller than the effect of external cues, and it's inconsistent across data sets. So it seems to be very context dependent. It's also somewhat curious that there wasn't a difference between factual and reasoning questions in terms of metacognitive ability. So introspectively, it seems much easier to say whether I know or don't know some particular fact about the world than to know whether I'll be able to figure out this reasoning question. Overall, so do these results suggest that we're on the path to LLM self-awareness? Well, so the fact that recent models and larger models generally do better suggests maybe, or generally show a higher signs of introspection, suggests maybe. But the task success actually, if you think back to that chart, that actually did not show a pattern. So it's possible that there's some sort of conflation going on where the models are getting better. They're getting better at uh, sort of having this signal and using it to maybe modulate their expressions of confidence, but due to personality training or due to the nature of the reasoning models, there maybe have a bias towards answering or other biases that actually make them do worse at applying this knowledge in real tasks. And so it's both the delegate game task success and also the second chance game change rates after controlling for these other factors did not show a very strong pattern of scaling with model abilities. So next steps here are interpretability, I think, is a natural one. We do see these. It does look like there's evidence of an internal signal being used in terms of what we see from the entropy. It would be nice to identify that and potentially control it. So one challenge here is that it shows up in the large models. That can make interpretability hard, but maybe we can create an analog of this signal by fine-tuning smaller models, creating model organisms of metacognition, as it were. Can also working on other paradigms, so ones perhaps that better equate baseline and test conditions, so that discourage this change the change rates that we saw. Is it possible to reduce the incentive to use external cues further? The one idea I've been toying with is fine-tuning in arbitrary knowledge. Also, there are other components of self-awareness that would be interesting to measure as well. And then finally, I've kind of appealed to intuition in some respects here, but it would be good to have human studies doing comparable experiments to establish a baseline to say, to allow us to say, relative to how humans can do on these various tasks, how far towards human level metacognition are these models. And so with that, I'll close and open the floor to any questions or discussion.